All right, kids. So now we're gonna go forward from this point onwards. Just wanna basically tell you that we learned about three systems yesterday: closed, one end open, one end closed. One end closed and two ends open. Just to give you a summary now, so that you guys remember the formulas, and then we're gonna look at some of the questions. So two ends closed, one end open, and two ends open. So for these ones, the formula for this is V equals to 2L over N, lambda equals 2L upon N, and F equals to V times N over 2L. And obviously, N would be 1, 2, 3, 4, and so on. For one end open, lambda will be of 4L over N, and frequency will be V times N over 4L. And then N will be 1, 3, 5, 7, so on. Then two ends open will be lambda equals to 2L upon N, frequency equals to V upon N over 2L, and N will be 1, 2, 3, 4, and so on. Yeah, bin bhi लेंगे, please. जी जी कावा. Now, with that said, let's have a look at some questions from there. So, wait. Stationary waves. Okay. Okay. All right. So we're going to look at the first question, which is this one. Let me just take a screenshot, and then I'm going to explain to you how these questions are dealt with. And then we'll also do the bottom one as well. Rest of you, I'll give it to you for practice. Okay. Okay, here you go. So now let's have a look. So in this one, it says a musical instrument is called a bugle. Is a long tube with one mouthpiece at one end, the other is open and flared. So the moment you see this means this is one and closed system. All right, kids. Then says a musician maintains a stationary sound wave with a node and mouthpiece and antinode at the other end. The lowest frequency of a bugle can produce 92 hertz, which means this is the fundamental frequency he's talking about. Now, the moment read this, I should remember the formula, which is the frequency. Because we want to find the frequency, we'll use this Vn over 4L. And I also know that it is 1, 3, 5, 7, it's odd numbers. So for the fundamental one, fundamental means the very first frequency, which is 1, which means F at fundamental frequency, which will be Vn over 4 times 1. Do you guys agree? Oh, my
Yes.
sorry. V1 over 4, like that. Now think about it this way. You have this formula, and at this frequency, we know the frequency is given as 92 hertz. So we get a value of 92 equals to V upon 4L. Now, if I want to find the next frequencies amongst these, so what do I need to do? I need to do V times N over 4L. V over 4L is 92 times N. So every time I put a value of N in this, I'm going to get the next frequency. The next frequency will be created at 3. So 92 times 3 is going to be what?
276.
276. Okay. So it means we can either have this one or this one. And then if I want to find the third harmonic, which is 92 times now 5, and that is
460.
460. Yeah. So the answer would be C. Do you guys get it?
Yes.
Okay. Now, so this is pretty easy if you just remember the formula. Otherwise, you will be, because v over 4l, like the velocity and the length is constant, so this is 92. So every formula will be v upon 4l times n. So 92 times n, 92 times then the next n, the next n, like that. Okay, Raza? Get it? All right. Now the next one, I want you guys to try this at least. Take 2 minutes. Try if you can do something about it, and then I'll explain if you don't understand. Use the same logic behind it, and then let's hope everything goes well. Yes, they do. Just 2 minutes. Take it out. See if you guys can have an answer. All right, you guys, you got any answers? No, that's bad. Now check this out. See that they've said that there is a tuning fork, and right now the length is 25. Length is 25, which you see. Now, a staging wave is set up in the tube when the same frequency as the tuning fork, right? And the lower end of the tube is sealed. When it is sealed, obviously it is a sort of a one end open, one end closed, which means again we have to use F equals to V n times 4F. And also, we should understand that it's basically n has to be like 1, 3, 5, 7, so on. Understood,
Yes.
everyone? Okay. Now think about it this way. It says the length that they have shown. This is the minimum length of tube with the lower end sealed creates a stationary wave, which means that at this length you will get a fundamental frequency. Do you get it?
Yes.
So I'm gonna make length the subject of the same equation. I'll put it here, and now I'll see when n is equal to 1, I get 25 here. So I'm going to put 25 equals to v times 1 over 4f. Understood? It says which other lengths of the tube sealed at lower end will also create the stationary wave. So we want the same fundamental frequency, but this time we got to change the length. Is that clear? So which
Yes.
means this whole thing is going to be 25. All right. So I'm going to write the equation again. L equals to Vn upon 4f. And then I'm going to put this whole thing is 25. So I'm going to write 25 times n. Now when I put 3 in this, so 25 times 3 is, I think, 75. So this
Yes.
could be the answer. And then 25 times 5 is, because the next number is 5. So that's going to be 125. So it has to be D. Understood like that.
Yes.
So you have to work around the same formula because these formulas are your lifesaver. Otherwise, you're pretty much, will be stuck in this. Get it?
Yes.
Okay, write this down, please. Raza, Shazeb, Asma, anything, Fatma, Imal, any questions you guys have?
So it's now more clear now.
Yeah, it's like the same thing with different variations, all right? They can give you another formulas as well, but this formula, because it's a tricky one, because it has odd numbers, so they believe that people will make more mistakes in this. That's why they give this more often. So you guys need to be aware of that. Okay. All right, kids. Should I go forward now, please?
Yes.
Yes, sir.
Now we have like three experiments to determine the speed of sound using stationary waves. So these experiments will both be asked in I mean, paper one and paper two. They're not really related to paper three. So finding the speed of sound using stationary waves. So first we're gonna use the first experiment is using a water column in a tube. So how do you do this? It's pretty simple. You wanna basically put a you want to put water inside a reservoir like that. Okay, this reservoir you can add in, remove water as well from it. So, or you can remove the tubes. So you gotta make a. You have to take a tube that is a hollow cylinder like this. All right, kids. Now, what you can do is you can actually, basically, you can move the tube up and down when you have a tuning fork. Tuning fork is basically a sort of an instrument that gives you a very specific frequency of sound. So if you go to some doctor to check your ears, they also use this. So suppose when you're moving it up and down, at one point you will hear the loudest sound, and then you say, okay, this is the height of the tube where a stationary wave has been formed because now you hear the loudest sound. Is that clear? So obviously, in this stationary wave, you will have a node where the water level is and antinode where the opening is. That's how you hear the loudest sound. And then what you do is you start moving this tube up and down. And now once you move it up, now at a new length, you will hear the next loud sound. So the next loud sound would be when the next antinode is formed, like that. So if this is the node, then this is also a node. This is also anternode. And then obviously the loud sound comes when you basically use a tuning fork like that. And then obviously this height would be some different height larger than before because you moved it up. So this is H2, this is H1. You can draw the diagram and then I'll explain how I've done this. Okay. So kids, then what happens is that when you're looking at this, just remember, just write that adjust the length h1 till you hear a loud sound. Then move the tube up or down till you hear another loud sound and note h2. So you want to find the new length. Furkan, why are you late, beta? This much late? Why? That's very bad, by the way. Now, the next thing you want to do is subtract H2 with H1. This will give you the difference between two adjacent antinodes. All right, kids. So basically, what I'm saying is that when you subtract length 1 with length 2, sorry, H1 with H2 in this, so what happens is that you're going to get the distance between node because once the node is formed at H1 and then the next is H2, so the difference between those would be equal to half lambda. So then we can say that this lambda can be 2 times the difference in height. Is that clear, everyone?
Yes.
And finally, use V equals to F lambda to find speed of sound, where F is the frequency of the tuning fork. Is that clear, everyone? So this is pretty simple, basic experiment. Again, I'm explaining this to you. You basically move it, like move up or down till you hear the first loud sound. You basically measure the height. Then what you do is you move it up, and then when you hear the next loud sound, you measure that length as well. You subtract both lengths, you're going to get the difference between the two antinodes right here. And then that distance is equal to half lambda. We've studied that. You can put it equals to basically V equals F lambda, and the frequency of the tuning forks are known. So from there, you can find the speed of sound. All right, kids?
Yes.
Yes, sir.
Write it down, please. Okay, done. Should I go forward now, please? Okay. Take your time. Okay, kids. Now should I go forward? You guys have written it?
Yes, sir.
Okay, good. So the next experiment we're going to discuss is basically called number 2 at the heading, please. It's called using a cathode ray oscilloscope. We have done cathode ray oscilloscope, hai na, in the previous chapter. And now you might have an idea how it works. It basically gives you time and can give you the voltage as well. So let's have a look at this. So what you do first is that you want to keep a reflecting surface It could be a metal, it could be anything, it doesn't really matter. And then you have to put a signal generator. This is a loud speaker. Connected to a signal generator of known frequency. Okay. Now you're going to set it up, and if it creates a stationary wave, like that. Oh my god. Like that. Okay, so it will create a station wave that you can't see, by the way, by naked eye. But then there is a use of it. So obviously, you know that at this point there's an antinode. Right now I'm drawing, so there's a node, and then an antinode, then a node, antinode. Okay, this is a bit weird. I have to basically make it smaller. Okay, so antinode, 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 like that. Do you guys understand that? Okay, kids. Now what you need is you need basically a CRO like that. So the CRO is made or connected with a microphone like that. All right, kids. Now what you're going to do is you guys need to understand that when the microphone is moved this way, this is your CRO. So the moment it is going to pass this point A, it means the CRO is going to show you the maximum amplitude, because CRO shows, you know, how much energy is there.
Say the displacement is the greatest at the antinode.
Yeah, the CRO shows vertical means the highest signal strength is going to be shown, right? So when the mic is made to move here, right? What will mic show? It will show you a zero reading, because now there's no energy, right? And then when the mic is moved to this point, right? The mic is going to show you again the highest reading. Do you get it? Like that. So on the CRO, you will see basically max amplitude here and here. Is that clear? Which basically means that if I could find the length between, or move the distance, if I could find the distance that I moved from this point to the next highest amplitude, I can basically find the wavelength. Do you get it?
So why is it max in n?
Sorry?
So you've pointed the arrow to the node and it's maximum.
No. I don't see this. I don't see the wave, right? What I notice is that if I grab the mic from here, okay? If I put the mic here, so it's gonna show me the maximum uh, amplitude on the CRO. Do you get it? Because anti-node has the maximum energy. Do you get it? Then,
Yes.
if I put it here, right, on the node, because I'm moving it this way, okay, like that. So if I move it here, I will see no reading because I see no reading because you see here there's no energy. But then if I keep on moving, now when the next antinode comes, so I move the distance d, and I'll see another maximum reading. Do you get it? So it means if I could find the distance I have moved from this point to this point, which is when the CRO shows two maximas, I can know that this is the antinode to antinode distance. Is that clear?
Yes.
Like that. So this is my idea in this that I'm using to find the speed of wave. You can't see the red wave or the antinode. You just have to see it from the CRO. Get it? Now let's write it down. So we're gonna say as we move the microphone along the line, the CRO detects zero amplitude at nodes and maximum amplitudes at the antinodes. Understood? Now measure the distance moved d between adjacent nodes or antinodes. It's up to you. Either you want to go from zero amplitude to zero or maximum. It's up to you. And then length between two adjacent nodes or antinodes will be equal to half lambda. Sorry, d will be equal to the half lambda. What you're going to do is you can find lambda by simply multiplying the distance by 2. Then use v equals to f lambda to find the speed of sound, where f is the frequency of signal generator. Is that clear, everyone? Yes. Asma and Fatima, Dania, Imal, you guys understand that?
Yes.
And Furkan, Raza, Shazir, the boys, you get, do you?
All good, sir.
Okay, Shazir, are you here, by the way? Okay, now, speaking about this then, we're gonna go forward now.
Yes, sir.
Okay.
So the reflecting surface be polished or
It should be, yeah, it should be like shiny polysilicon. Otherwise, don't do anything. Okay.
Yes.
Okay. The next would be, I just want to put a note here, so you guys also write that. And basically, you can also use the same method, can be used for finding speed of electromagnetic waves, right? We can use a and a probe and a particular wave, such as microwaves instead, right? So we can basically find the speed of EM waves, which is speed of light, really. So you can basically write that down as well.
So sound waves are not transverse. So how do you compare the drawing that you give, the transverse wave to the longitudinal wave?
Sound waves and the longitudinal transverse wave both can create stationary waves. I'm going to show you with the drawing how. Okay? Don't worry about that. Yeah. They both can create that. This is why we can use the same method for both. Okay.
Yes.
Okay, when you've done this, then I'd like to go to the next method.
So do we need to know how the probe or the sensor works in this for EM waves?
Probe means like mic is to sound, probe is to catch microwaves or infrared and stuff like that. You understand?
So could you repeat it?
Like what I'm saying is like microwaves, sound waves can be detected by the microphone, right? So microwaves can be detected by its own probe.
Okay.
Yeah. Understood? Should I go forward now then?
Yes.
Okay. Now, the next method that we're going to discuss is called Kunz Kunz dust experiment. Now, this experiment is done through you have to put a speaker inside a pipe. So let's suppose the pipe is like this. And then you have to put a loudspeaker like that. This is a loudspeaker connected to signal generator of known frequency. All right. So when the station waves are formed, like that, inside this tube, right? So, well, this doesn't look very good. Let me try to make nice runs. Ah, crap. Sorry. Oh my god. By the way, this experiment can also be done with fire and other stuff. Anyway, I just want to tell you when station waves are formed inside. You basically have dust inside, all right? So the dust particles, they like basically put boric powder. Do you know what boric powder is? Boric powder is like very fine powder that, if you know, in Pakistan, a lot of people play carom board. Have you played that game?
Yes.
Yes.
So the powder that we put on the top of it to make the discs slippery, this is the same powder we put it because it's very light. This powder basically forms heaps underneath the nodes. Like you can't see the wave, but you can see the heaps. Why heaps are formed? Because you see, it gets the particles get displaced by the high energy antinodes, and because nodes have no energy, the heaps of dust just settle there because there's no frequency, there's no energy. You get it like that. So these would be your dust heaps, and then it is very simple. What you do, wherever the dust heaps are, we already know that these are the nodes because otherwise dust heaps cannot form, right? Now we know the location of the nodes. So what you do is you can simply find the length between adjacent nodes, and then use this length to find the wavelength. So it's pretty simple. Now let's write it down. When signal generator forms a stationary wave, antinodes displaces the dust and beneath the nodes it forms heaps of dust. And why does it do that? Because because as nodes have no energy to displace, then you got to measure the length L of length L between two adjacent nodes and use V equals to F lambda, where lambda will be equals to 2 times L, as you know it's node to node, and frequency is frequency of signal generator to find the speed of sound. If you have any questions, ask me. Otherwise, please write this down. Very simple experiment as well. is everything is clear? So now I guess this would be all for today then. Tomorrow we'll start